start this lesson out with a predicament, I guess. I don't know. You're a landscape architect, and you're designing a deck. Your client has already bought these nice little lounge chairs that they wish to place on your deck. You want to make sure that you place those lounge chairs in the largest angle possible, giving that person room. You can put a side table. We'll really let them lounge. So, if you're not carrying a protractor around you with you in your pocket, how could you determine what the two biggest corners are? So what we're going to learn today is that the sides give us clues about the angles, and the angles give us clues about the sides. I can't use a side to find the measure of the angle. I don't know the measure of angle B, but I can use the sides to determine what angle is the largest and what angle is the smallest. So, everyone do this. What is the distance? Everyone do it. Yep, you have to do it. No, Hatham, that only works on right triangles. We're not doing Pythagorean theorem. Okay. Yes, y'all are right. The distance between my fingertips right now is 0. Okay? 0, right? And in the angle that I'm opening, the angle is also 0. I have not created anything yet. Now, I'm going to open it a tiny bit. That is a very acute angle. It's a small angle. And the distance between my fingertips is what, like 3 inches or something? Not very large. Now, as I open my angle more and more, as my angle increases, what happens to the distance between my fingertips? Yes. So a larger angle will produce a larger distance between my fingertips. And a smaller angle will produce a smaller distance between my fingertips. So what that's saying is that this angle is going to have to open wider the longer the side opposite to that angle. So not the sides next to, the side opposite. The bigger AC is, the bigger B has to open up to it. The smaller AC is, or BC is the smallest, then the smaller the angle has to be to open up to it. So, if we look at this picture and we want to find the two biggest corners, first, we find the two longest sides, and then we look across from those sides. What angle is opening up to 27? It's B. What angle is opening up to 21? It is C. So our two largest corners or angles would be angle B and angle C. Yep, okay. So it's called something. It's kind of a corollary to the triangle inequality theorem, but go ahead and write it down. There is a relationship between the sides and angles of a triangle. A side can't find the angle for me, but it sure can find out which one is the largest, the medium, and the smallest. So I'll give you a minute to put that in your notes. Let's see if we can try it in some examples. That is the name of the side to the triangle. So we're going to try to label this triangle in its sides with shortest, medium, and longest. What do you think would be step 1 here? What would we have to investigate first? Yeah, that's right. Find the third angle. And good job. You're trying to use vocab, but this triangle doesn't have any vocab because we don't know what kind of triangle it is. So find the remaining angle using triangle sum theorem. Okay, what is it? Thank you. 56. Good job. So the remaining angle is 56. And now we find, it doesn't really matter which one you find first. Find the smallest angle. Okay, you win. You're the smallest. It will be opening up to the shortest side. Find the medium angle. You win, 58. You're the medium. It will open up to the medium side. And then, of course, this largest angle will open up to the longest side. All right, go ahead and try this example. You will probably want to sketch your own triangle. And then I want you to list the angles from smallest to largest. Step 1 of this problem, sketch a quick triangle. We've got R, we've got M, and we have F. RM is 8, MF is 5, and RF is 6. List the angles from smallest to largest. since there's only one triangle involved, there's not multiple vertices, not a vertice with different angles at it, we can use one letter. We can use one letter each. So we look at the shortest side, and it's across from the smallest angle. So you would write the angle symbol and then a capital R, angle R. The medium side would be across from the medium angle. So you would do angle symbol M. And then, of course, the largest side would be across from the largest angle. So the answer was angle R, angle M, angle F, in that order. You don't name the sides, because I gave you sides. You name the angle, the thing I didn't give you. To name an angle, you can use one letter, or you can use three letters. All right, go ahead and try this one. Now we're going to list sides, not angles. List these sides from shortest to longest. Okay, guys, let's do it. What was the missing angle? What did you get for angle I? Ooh, I already have two different answers. 33. Okie dokie. So the concept is not hard. Actually, probably the hardest part of this problem is using correct notation, right? Okay, shortest to longest. So we're not going to use our eyes. We're going to use the data. We're not going to just look at which one looks shortest. We're going to decide based off of the angles which one is supposed to be the shortest. The medium. And of course, everyone put IW last, right? Or WI. That's how you name a side, two capital letters with a segment on top. Make sure they are capitals. And remember, when you're naming a segment, the order doesn't matter. BW and WB are the same segment. Okay, let's take a look at our second real-world problem, and we'll get into our second common sense theorem of the day. So here we have a drawbridge that spans over the Chicago River in Illinois. How a drawbridge works, obviously, is we take a look at the distance between these two supports. Let's call that side, that would be C. If I take a look at the length of C, how should the length of A and B compare to the length of C? How should the length of A and B compare to the length of C? Ooh, Sharon got it. You know, it wouldn't matter which one's longer, which one's shorter. A could be shorter, B could be shorter, they could be different lengths. But what would matter is for this drawbridge to work correctly, we would want A plus B to equal C. That way, when the drawbridge was closing, it creates a perfect segment with no gaps or spaces, a segment, right? Not a triangle, but a segment. Now, what would happen if A plus B was greater than C? What would happen in the real world? What would the consequence be? That's what I was looking for. They would hit each other. You just hear the... As they were closing, they would crash into each other. There would probably be some damage. It would not be a bridge anymore. It would be like a skateboard park or something. I don't know. It would not be a bridge. A plus B should not be greater than C. Now, what would happen if A plus B was less than C? There would be a gap, right? Now, if it was a tiny gap, it might not matter, right? A few inches might not make a big difference. But if the gap was large enough, then there could be cars falling into the river. We don't want that. So what's important to understand is that when we add two of the sides of a triangle, what do you think needs to be true compared to the third side? If we want to make a triangle, since we're in the triangle unit, which one of these created a triangle? Nope, the first one created a segment because we wanted our bridge to be a flat, nice road, a segment. The second one created a triangle. And the third one really created nothing. It was just like two sides that wouldn't even touch each other. So it wouldn't really create anything of use to us. All right, let's look at that in a little bit different of a light. Take a look at this triangle. I'm going to add up the two sides, and I'm going to compare it to the third side. 15 is greater than 10. Everyone agrees, right? Let's do it again. 13 is greater than 10, but my triangle got shorter, but okay, it's still a triangle. Awesome. 5.5 plus 6.5. Still greater than 10. Getting shorter, still a triangle, but squatty little triangle. 11. Still greater than 10. Still a triangle, although one of the most obtuse triangles we could ever create. So what happens when I go down one more? Oh my goodness. So my conclusion is that when I add two sides of a triangle, the sum has to be greater than the third side, right? If it's not greater, if it's equal to, we do not have a triangle. This is not a triangle. That is a segment. That's the drawbridge right there, okay? So that's actually the triangle inequality theorem. When you add any two sides of a triangle together, the sum needs to be greater than the third side. Yep, no cars falling into water for us. When you add two sides of a triangle together, the sum must be greater, than the third side. Sorry guys, it happens. You knew it was 10. The bottom was 10 the whole time. 11 is not greater than 11. All right, so please write down the triangle inequality theorem. You can take any two sides of a triangle, you can add them together, and you will get a result that is greater than the third side. It doesn't just work for the two sides we were looking at in the previous slide. It works for any two sides. This doesn't just work for a certain type of triangles, right, or isosceles. It works for every triangle. Okay, let's just do a couple examples really quickly, and you can start your quiz. Will these side lengths form a triangle? So here's what you do. Circle the biggest one. Circle the biggest one. Circle the biggest one. Circle the biggest one. Okay, you take your two smallest, you add them together, and you decide is that greater than or less than your third one. If they add up to be greater, keyword greater, then yes, you have a triangle. But in this example, we've got 10, we've got 3 plus 6, that's 9. 9 won't reach. 3 is trying to reach to 6, but it has to span across 10, and 9 is not enough to reach, so it will be a gap. So no, there's no triangle created. 2 plus 7 is 9. 9 equals 9. That'll create a segment. It will not create a triangle. Our largest side is 3a. Let's add these together. Ooh, that's 4a. 4a is greater than 3a, so that's another yes. Last example that we're going to do together. Two sides of a triangle have lengths 8 and 10. What are the possible lengths for the third side? So quickly, to do this, you take your two sides and you add them together. 18, that is your max. Then you take your two sides and you subtract them. 2, that's your min. So your third side, I'm going to call it S for side, is less than 18 and greater than 2. There's a whole range of possibilities. That third side could be 7, it could be 15, it could be 2.5. It could be anything that's greater than 2 and less than 18. How did we get 2 and 18? We added and we subtracted. Easy stuff. Find the longest side of triangle ABC if, okay, well first I noticed there's no picture drawn. We do not function without pictures, without diagrams, so we draw our own ones not given to us. The measure of angle A is 70. The measure of angle B is 2x minus 10 degrees. And the measure of angle C is 3x plus 20. So in order to find the longest side, I need to know the largest angle. To know the largest angle, I'm going to have to use good old triangle sum theorem. So let's add up these angles. Let's see, 2x plus 3x is 5x. 20 plus 70 is 90. Minus 10 is 80. So I added up, this is the sum I'm going to plug that back in. 2 times 20 minus 10. So that's a small angle. That's a 30-degree angle. 3 times 20 plus 20. And that's an 80-degree angle. So find the longest side. I take the largest angle and I look across from the largest angle. So the answer to that question was side AB, segment AB. Given triangle HAL, AH is greater than AL and AL is greater than HL. List the angles from smallest to largest. Once again, we want to draw ourselves a diagram. A, H, L. When I'm not given like concrete evidence, I like to make up numbers. Let's just make up a number for that first side. AH. It'll be 3. Well, it might need to be bigger than that because it's the greater one. Let's do 10. So 10 is greater than AL. AL is less than 10. So maybe we'll make that one 7. And then AL is greater than, 7 is greater than HL. So we need to go smaller than 7. Let's go 5. There we go. So those are not the side lengths of the triangle, but those are made up ones to represent the side lengths. Now I need to list the angles from smallest to largest. Smallest side is across from the smallest angle. So I don't know what HL equals, but I do know it's the smallest side because I made up numbers to help me. I could have also just listed the sides using these right here. I could have listed them from smallest to largest. My medium angle would be H, and my largest angle would be L, appropriately. L for largest angle. Last example of the day. This one you'll see in your homework. Arrange the letters' values from least to greatest. So what I notice here is that I've got 2 triangles going on, and one is noticeably smaller than the other. So what I'm going to do is start with my smaller triangle. I'm going to start here, and I'm going to start to list the sides from least to greatest, and hopefully this one will be when I switch over from my small one to my large one. Well, let's go ahead and find those missing angles just to be safe, even though we kind of know what they are. 19 plus 77, subtract it from 180. We know that that's the largest angle. And then 33 plus 22, obviously this one's going to be our largest angle. Okay, so I just did triangle sum theorem twice just to confirm that those were our biggest angles. So if you look in this first triangle first, the smallest side is the one across from 19. So A is the smallest, the least. The medium side would be E, and the largest side would be G. Okay, we are done with the small triangle. We hope that the largest side of that small triangle is the smallest side of our large triangle, because if there's overlapping, then we actually can't answer this problem with certainty. But it is. Look, 22 is the smallest angle, so G is the smallest one, so we're going to start with G. The next biggest one would be across from 33, so we would go F. And then, of course, the largest side in the whole picture would be L. So it was trying to spell eagles, but didn't quite. That would have been too easy if it spelled it perfectly. All right.